Now let us go for question number 11. It is about electromotive force, shortly written as EMF, electromotive force, and its source. My dears, before you understand any more, let me give you a warning. This word does not indicate force. Though there is a force in this name, there is a word force in the name, it is not a force. Please don't get confused. It is not a force. Very shortly speaking, it is energy per unit charge. Okay? So its unit would be joule per coulomb. Correct? It is not a force. Otherwise, its unit would have been Newton. But because it is not a force, its unit is not Newton. Its unit is joule per coulomb, that is volt. Correct? Fine. Please don't get confused. Now, what do you mean by electromotive force? What do you mean by its source? I am showing you. Tell me, if you want to have electric current in a circuit, what will you do? You have to bring the charges in motion, because when charges are moving, at that time they constitute electric current. But tell me, when the charges will come in motion, provided work is done on them, provided energy is given to them. Correct? So you need to have some device with the help of which you can give energy to those charges. Such a device with the help of which we supply energy to the charges, and thereby we have production of electric current, itself is known as source of EMF. Correct? Fine. A device with the help of which we can supply energy to the charges is called source of EMF. Correct? Now in practice, we can supply energy to the charges in different ways. Which different ways? I am showing you. You can supply energy to the charges through chemical forces. You can supply energy to the charges through magnetic forces. You can supply energy to the charges through forces due to temperature difference also. Correct? Depending upon which method you are adopting, you may have different types of sources of EMF. Okay? Fine. Now in the present article, we will study that source of EMF in which energy is supplied to the charges through chemical forces. Correct? How? I am showing you. Now let us go for definition of electromotive force of electric cell or battery. If it is only one such device, we call it electric cell. But if you have got group of electric cells, then normally we call it battery. Okay? Now onwards, majority of the times we will use the word battery in general. Okay? Fine. Now what do you mean by electromotive force of a given battery? Let me show you. Its symbol is capital E. Don't write capital E the way you are writing for electric field. No, you have to write capital E very specifically this way. This is the capital letter from third ABCD. Okay, capital E. Write it this way. Please be very careful for putting the symbols. It's a question of your impression during examination. To understand about electromotive force of a given battery, you please consider some electrochemical cell. You must have remembered from chemistry a device with the help of which chemical energy can be converted into electrical energy is known as electrochemical cell. Correct? Fine. So just think of some electrochemical cell in this box. Here I am showing you the line diagram of a battery in the open circuit condition. Why its condition is called open circuit condition, I will explain. Okay? Fine. So there is some electrochemical cell inside this box. Now tell me, in this electrochemical cell, what happens? The chemical reactions are taking place between the active reactants. Correct? Fine. as a result of those chemical reactions, you know what happens? Energy is given to the unlike charges. Energy is given to unlike charges which are liberated in those processes. Unlike charges means positive as well as negative. But work is done on those unlike charges in such a manner that chemical forces are exerted on those unlike charges in just opposite directions. So, if chemical force exerted on a positive charge is in this direction, then chemical force exerted on negative charge will be in this direction. Okay, fine. That is what I have shown in the figure now. Look, on a positive charge, chemical force is exerted, suppose this way. Then on a negative charge, chemical force will be exerted just in opposite direction. Correct? Tell me, what are these forces? As I said just now, they are chemical forces. Chemical means not electrical. Not electrical, that's why we call them non-electrical forces, and that's why the symbol is Fn. N stands for non-electrical. Okay? Here I have written Fn means non-electrical force. Non-electrical force, and here they are chemical forces. Got it? Fine. Now tell me, if positive charge happens to move in this direction, then it will be reaching to this terminal, this end of a electrochemical cell. Fine. We call it, say, pole A or terminal A. Now, if positive charge is accumulated here, naturally this pole will become positive. So, I am showing you plus sign. Fine. Similarly, if negative charge is accumulated here, will make this pole negative. That's why I am putting minus sign. Okay. Once this pole becomes positive, this pole becomes negative. Tell me, there is an electric field generated between these two poles, and you know direction of electric field, it will be from higher potential to lower potential, from positive to negative. So, in this direction we have now electric field. Okay, fine. Now tell me, if chemical processes are going on continuously you will have liberation of positive and negative charges. Continuously you will have liberation of positive and negative charges. So, when another positive charge is trying to go this way under the influence of this non-electrical force, at that time tell me what this positive potential will do on this pole, will try to repel that positive charge, correct? So, when this tries to repel this positive charge, it will exert some force which is nothing but electric force, and that electric force I have shown by symbol Fe, correct? E for electrical. Simple? Fine. Now, you know direction of electric force exerted on a positive charge is in the direction of electric field. Electric field is this way. So, in the same direction there would be electric force. But so far direction of electric force exerted on a negative charge is concerned, you know it is opposite to direction of electric field. Electric field is this way. In just opposite direction there will be electric force exerted on this negative charge which is trying to approach this negative pole, correct? Fine. So, what I mean to say, as time passes on, as further and further chemical reactions are going on, there would be more and more liberation of positive and negative charges, but then as more and more positive charges are accumulated here, this pole will gain more and more positive potential. Then similarly here more and more negative potential. I mean to say potential difference between these two will go on increasing with time. When potential difference increases, the strength of electric field between these two poles will also increase, and when strength of electric field is increasing, then this electric forces also will increase in magnitude, correct? Now tell me, so far these non-electrical forces are concerned, its value is constant, but so far value of electric force is concerned, its value goes on increasing with time. A stage will come when this value will become equal to this value, that is Fe will become equal to Fn. These two oppositely directed forces will become equal in magnitude. At that time, Fn equals to Fe, Fn equals to Fe. See here, initially Fn was greater than Fe, that is, non-electrical force was greater and electric force was smaller. Why electric force was smaller? Because initially we had accumulation of less amount of positive charges here, less amount of negative charges here. So the potential difference between these two was less, and so the strength of electric field between these two was less, and because electric field was weak at that time, electric forces were also smaller in magnitude, correct? But as time passes on, we have liberation of more and more positive and negative charges through the chemical processes. Then as time passes on, here there will be accumulation of more and more positive charges, here there will be accumulation of more and more negative charges, and because of that, potential difference between these two poles will go on increasing, and because of that, strength of electric field will also go on increasing, and because of that, electric force also will increase in magnitude. So earlier Fe was smaller, but as it increases in magnitude, at one stage the value of Fe becomes equal to value of Fn, correct? And you can see in the diagram, these two forces are oppositely directed, and if their magnitudes become equal, then the resultant force exerted on the moving charge would become 0. So at this stage and then after, there won't be any movement of positive and negative charges inside the electrochemical cell, correct? Then tell me, when there is no movement of charges inside the cell, meaning thereby there is no current, and when there is no current inside the cell, at that time whatever potential difference we have between these two poles, that same potential difference itself is known as electromotive force of a battery. It is called electromotive force of a battery, shown by symbol capital E. Then very simply speaking, if you want to define EMF of a battery, you can simply define it this way. When there is no current through a given battery, that time potential difference between its two poles or its two terminals is called its EMF. When there is no current through a given battery, the potential difference between its two terminals is called its EMF, shown by symbol capital E, correct? Fine. Now when there is no current inside the battery, we say that battery is lying in a typical condition called open circuit condition, open circuit condition, open circuit condition, okay? If you got a closed circuit, that time current is flowing, but if you just break that circuit and you make it open, then there won't be any current. Similar situation is arising here. There is no current through the battery, so we say as if that battery is in the open circuit condition, correct? For a battery lying in an open circuit condition, whatever is the potential difference between its two terminals, same is known as its EMF, okay? Let us have some more definitions, some more equivalent definitions of EMF of a battery. I am showing you. Suppose this battery has achieved equilibrium condition, correct? So there is no current, okay? Now tell me, just consider a charge, say positive charge plus a small q at this negative terminal, correct? Now suppose that positive charge wants to get transferred from this pole to this pole, from negative pole to positive pole, correct? And for that it is to be moved this way. Now tell me, this is a positive charge, this is a positive terminal. Can you tell me with a common sense, can this positive charge itself, can it move this way towards this positive terminal? No, it cannot move because this will repel this, correct? But then also, if we want to have motion of this positive charge from here to here, then what we need to do some work. don't bother. We don't have to do that work. We don't have to do that work. That work will be done by this battery. Work will be done by this battery. Just consider this way, as if here it is a closed circuit, correct? Then for a closed circuit, what is the direction of flow of electrons? It will be from negative to positive terminal this way, correct? Then where will be the direction of electric current? Just opposite, it will be this way, correct? As if it is in the direction of flow of positive charges. Conventional direction of electric current is in the direction of motion of positive charges. So at that time, that positive charge will be forcefully shifted from here to here by this battery. At that time, some work is done by that battery, and that work done on this charge Q is suppose capital W, capital W. How would you find out this work done? Very simple. You have studied in 11th standard, work done by a variable force is nothing but line integration of that variable force over a given path. Okay? You may choose any path joining this negative and positive pole. Then on that path you are supposed to take line integration of that force. Which force is shifting this charge from here to here? This force. This force will bring this charge from here to here. And what is this force? Non-electrical force. That's why I am putting the symbol vector Fn. Correct? So when you find out line integration of non-electrical force over a given path joining negative and positive pole of a battery, you will get amount of work done. Correct? Don't bother for the shape of the path, because this work done does not depend on the shape of the path. Okay? Fine. But mind well, because you are taking this line integration from here to here, I am just putting the lower and upper limit like negative and positive. From negative pole to positive pole, correct? And now on charge Q, if amount of work done by battery is capital W, then on a unit positive charge, what should be the amount of work done? This into this upon this. This into this, that is W upon Q, W upon Q. Tell me, very shortly speaking, what will this ratio give me? It will give me amount of work done per 1 unit positive charge. And the same ratio itself is known as electromotive force of a given battery, shown by symbol capital E. Correct? Now you can just place the value of W, which is this much. I just put it over here. Correct? Fine. Upon Q. How would you define electromotive force using this expression? Very simple. Amount of work done by a given battery in order to shift 1 unit positive charge from its negative to positive terminal inside the battery is called EMF of that battery. From this expression, you can define EMF of a given battery this way. Amount of work done by non-electrical force on a unit positive charge while pushing it from negative to positive terminal inside a given battery is called its EMF. I repeat, amount of work done by non-electrical forces on a unit positive charge while pushing it from negative to positive terminal inside a given battery is called its EMF, shown by symbol E. Correct? Fine. Now from this you can find out the unit of EMF, very simple. Unit of work, it is joule. Unit of charge is coulomb. Joule per coulomb, you know, it is renamed in SI unit system as volt. Okay? 1 joule per coulomb is 1 volt. Correct? Do you know what is the EMF value for a pencil cell? It is 1.5 volt. 1.5 volt. 1.5 volt means what? 1.5 joule per coulomb. Meaning thereby, when you employ that cell inside a closed circuit, then for every 1 coulomb of charge, when it is pushed inside the battery from negative to positive terminal, it will supply 1.5 joules of energy. Got it? Fine. Now from this you can find out dimensional formula for EMF. It is dimensional formula of work divided by dimensional formula of charge. For work, remembered from 11th standard, m raised to 1, l raised to 2, t raised to minus 2. Here it is. For charge, it is current into time, so it is a raised to 1, t raised to 1. Correct? Now, m raised to 1 as it is, l raised to 2 also as it is, t raised to minus 2 minus 1, that is minus 3, a raised to 1 going up will become a raised to minus 1. Correct? So, altogether this is the dimensional formula for electromotive force, and same is the dimensional formula for potential difference also, same is the dimensional formula for voltage also. Correct? Because whatever you are taking into consideration, whether potential difference or voltage or EMF, all of them have same unit, that is volt. Correct? Fine. Now tell me, we have talked about open circuit condition. Open circuit condition, at that time, whatever is the potential difference between its two terminals A and B, let it be shown by symbol VAB. Correct? And now onwards we will show it by symbol only capital V. But what does it indicate? Potential difference or voltage between two terminals A and B. Voltage between two terminals, that is why we have given another name to that voltage. We call it terminal voltage of a battery. What do we call it? Terminal voltage of a battery. Terminal voltage of a battery. Correct? It is nothing but voltage between its two terminals. That is all. Now let us talk about closed circuit condition. Closed circuit condition. If the same battery is now placed in a closed circuit, you may do one thing, you may just join these two ends, correct? And in between you can just have some external resistance, okay? Let it be capital R. So this is how the path is made closed. Now this positive terminal I am showing by this longer line segment symbolically, and this negative terminal is shown by a shorter line segment. This is how we show the symbol of a battery. Longer terminal means positive terminal, shorter terminal means negative terminal. Okay. Have you noticed something extra which are shown in the diagram? It is about small r. Now what is this resistance? You can see this is the symbol of resistance. It is some sort of resistance. What is that? It is nothing but internal resistance of this battery. Internal resistance of a battery, shown by symbol small r. Now let me talk about internal resistance. We now go for internal resistance of a battery, shown by symbol small r. When these positive charges are pushed from negative to positive terminal by this battery, at that time they will have to pass through the materials which are used inside the battery. And I told you, every material has got a specific property by the virtue of which it opposes the drifting motion of charges inside it, and that very specific property is called its resistance. Here whatever resistance is arising from within the battery, we call its internal resistance, shown by symbol small r. Okay. Remember, every battery has got some internal resistance. No doubt it is very small, but it is never 0. It is very small, but it is never 0. Correct? Fine. Now if this battery is in the form of a electrochemical cell, then for electrochemical cell its internal resistance small r depends on which factors I am showing you. It depends on these three factors. Look, first, concentration of an electrolyte. It depends on concentration of an electrolyte. Second, it depends on distance between this anode and cathode. Normally we take this positive terminal to be anode and negative terminal to be cathode. So internal resistance depends on distance between positive and negative terminal. Fine. That is, it depends on the distance between anode and cathode. And last, it depends on the area of parts of anode and cathode immersed in an electrolyte. You must have remembered from chemistry, in the electrolyte we have electrodes partly immersed inside the electrolyte. then this internal resistance depends on the surface area of the immersed parts of electrodes. Okay. So, on these three factors the internal resistance of electrochemical cell depends. Okay. Once again I remind you, every battery has got some internal resistance, no doubt it is very small, but it is never 0. Okay. So, now here the amount of energy supplied by this battery to this 1 unit positive charge when it is pushed from negative to positive terminal by this battery, that energy is known as its EMF. So, amount of energy supplied is capital E. How much amount of energy supplied? Capital E. Total energy gained by 1 unit positive charge while passing through a battery, that is called its EMF, which is capital E. Okay, fine. So, when this charge is pushed from here to here, total energy supplied by this battery is capital E. But now tell me, as this 1 unit positive charge happens to pass through this internal resistance, at that time that charge will require to do some work against this internal resistance. So, when the charge itself is doing the work, it will lose some part of its obtained energy, correct. Whatever amount of energy it has gained, out of which some part will be lost by that charge, because it has to do work against the internal resistance. Now, what part of energy is lost by that charge? I am showing you. Let us find out now amount of work done against internal resistance, and that amount of work done will give us how much amount of energy is spent by the charge while doing work against internal resistance. Let us find out. Let it be W dash. It is nothing but potential difference between these two terminals, that is between A and B, that is why I am putting the symbol VAB multiplied by charge. Potential difference multiplied by charge will give you amount of work done. Fine. At present you are talking about potential difference between terminals A and B, but between A and B, tell me what do you find here? Internal resistance, correct. So, it will be as good as potential difference across this internal resistance. And don't you know from Ohm's law, what is the potential difference across any resistor? It is nothing but current into resistance, current is I. Right now we are talking about internal resistance, whose symbol is small r, and what amount of charge you have taken into consideration? Right now it is 1 coulomb, correct, that is 1 unit positive charge. So, Q is 1. So, IR into 1, that is IR. So, this much amount of work is done by that 1 unit charge against internal resistance, and whatever amount of work is done, same amount of energy will get spent. So, this much amount of energy is lost by that charge when it comes here, correct. So, when 1 unit positive charge will come out of positive terminal of a given battery, at that time it will have energy left in balance. Net amount of energy left in balance will be E minus IR. Here I have written net amount of energy of 1 unit positive charge when it comes out of positive terminal of a given battery will be E minus IR. Why? Just now I told you, what is the total energy supplied by this battery when this charge comes from here to here? That is capital E, its EMF, but out of supplied energy capital E, IR amount of energy is spent by the charge while doing work against this internal resistance. So, that much is the loss of energy. So, out of gained amount of energy, you just subtract lost amount of energy, then you get net amount of energy left with 1 unit positive charge when it comes out of this positive terminal. Okay? That net amount will be E minus IR. And tell me, this net amount of energy will also give you potential difference between these two terminals A and B, that is why I am putting symbol VAB, and potential difference between two terminals itself is known as terminal voltage. I am putting symbol V. Okay. So, what is the relation you got? V equals to E minus IR. V equals to E minus IR. Okay. Please remember, this is the relation which is to be used only when the battery is in the closed circuit condition, and that too when it is getting discharged. Why it is said to be getting discharged? Because the current is flowing away from positive terminal. At the time, energy is used gradually more and more from this battery. When you are withdrawing current from the battery, when you are just using the energy from the battery, at that time this battery is said to be getting discharged. At that time, this relation holds good, which is V equals to E minus IR. Once again recall, what do you mean by open circuit condition? Open circuit condition is that in which there is no current through the battery, so I equals to 0. Put I equal to 0 here. When you put I equal to 0, V equals to E, V equals to E. So if you want to define EMF of a given battery in a very simple way, then that most simplest way is this: potential difference across the two terminals of a battery lying in open circuit condition is called its EMF. Potential difference between two terminals of a given battery lying in the open circuit condition is called its EMF. Simple? Fine. Now, if you have battery in a closed circuit condition, then in a closed circuit condition, some current is definitely flowing. So, I is not 0. And when I is not 0, at that time, you can have two possibilities. Either current may flow away from positive terminal, or current may flow towards the positive terminal. If current is flowing away from positive terminal, we say battery is getting discharged. At that time, this is the relation. Okay, V equals to E minus IR. I have written here, V equals to E minus IR. And then from this relation we can say that V is less than E. V is less than E, because neither I is 0 nor R is 0, so V will be less than E. But if you have passed the current this way, suppose you are connecting this battery with another battery whose EMF is higher than this, then current will be flowing in this direction. If current is flowing in this direction, then current is flowing towards the positive terminal of this battery. At that time, this battery is getting charged up. So during charging process, remember, you are supposed to use this equation, V equals to E plus IR. Instead of minus, now you must write plus sign. Okay, so I written here, during charging process, V equals to E plus IR. Here also, when I is not 0, R is not 0, you can write V is greater than E. V is greater than E. Okay. For example, if this voltage is, this EMF is 1.5 volt, and this voltage across internal resistance is suppose 0.1 volt, then 1.5 minus 0.1, that is 1.4. So this 1.4 will be less than 1.5. So I am writing here V less than E. But here, if this is 1.5 and this is 0.1, then 1.5 plus 0.1, that is 1.6. So this will be 1.6, which will be greater than 1.5, correct? So at that time, V is greater than E. Okay. Let me summarize. If you have got a battery in open circuit condition, then V equals to E, correct? But if you got battery in a closed circuit condition, then V is not equal to E. When V is not equal to E, you can have two possibilities, either V less than E or V greater than E. When V is less than E, during discharging process, correct? And when V is greater than E, during charging process. Got it? Fine. So terminal voltage of a battery can be equal to its EMF, can be less than its EMF, and can be greater than its EMF. Okay, fine. We now go for question number 12. It is extra question worth asking in the school examination, not directly given in the textbook. Please just pay attention very nicely. Give some points of differences between EMF of a battery and terminal voltage of a battery. EMF of a battery and terminal voltage of a battery. Fine. Come on. EMF is shown by symbol capital E, terminal voltage by symbol capital V. Let us see some points of differences one by one. First, EMF of a given battery indicates total energy supplied to 1 unit positive charge when it is pushed from negative to positive terminal inside the battery, correct? Fine. So, it gives you total amount of energy, fine. But what about terminal voltage? It will give you net amount of energy left in balance with 1 unit positive charge when it comes out of positive terminal of a given battery. So, this gives total energy, this gives net amount of energy. That is the first point of difference. Second, this EMF does not depend on internal resistance. EMF of a given battery does not depend on its internal resistance, whereas terminal voltage depends on internal resistance. You may ask how, I am showing you. Here I have written note for that. According to Ohm's law, in a single loop circuit, remember, current is equivalent EMF divided by equivalent resistance, or you can say effective EMF divided by equivalent resistance. Here effective EMF is E and equivalent resistance. In this loop, there is a series connection of these two resistances. What is called series connection? We will see in the next lecture, okay? But there the equivalent resistance is simply summation of two individual resistances. So, just add up these two values. So, it is R plus R. That is written here R plus R. I repeat, current equals to effective EMF divided by equivalent resistance, okay? Now, during this discharging condition of this battery lying in a closed circuit condition, you know the relation is V equals to E minus IR. When V equals to E minus IR, just put this value of I over here, put it here. Come on, E as it is, minus as it is, I is E upon R plus R, E upon R plus R into small r. Now take LCM here, so it will be E into capital R plus E into small r minus E into small r divided by capital R plus small r. So in the numerator, E into small r and minus E into small r will get cancelled, left is E into capital R upon R plus R. Now from this relation you can see terminal voltage depends on internal resistance. Terminal voltage depends on internal resistance. So I am writing here, this depends on, this terminal voltage depends on internal resistance, okay. EMF of a given battery does not depend on external resistance. EMF of a given battery does not depend on external resistance, whereas terminal voltage depends on external resistance, okay. I am putting right mark here, terminal voltage depends on external resistance. EMF of a given battery is constant. EMF of a given battery is constant, but so far the terminal voltage is concerned, it is found to be variable. Its value will depend on the condition of a battery, whether it is in open circuit condition or in closed circuit condition. In closed circuit condition also there are two possibilities, whether it is getting discharged or it is becoming charged up, okay. Let us see in all the cases what is the value of V, I am showing you. For OCC, that is open circuit condition, just now I told you V equals to E, V equals to E, here I have written. For open circuit condition, V equals to E. For open circuit condition, V equals to E, correct? Here it is, V equals to E. For closed circuit condition, CCC, V is not equal to E, V is not equal to E, correct? At that time you can have two possibilities, whether battery is getting discharged or getting charged. Come on, during discharging V less than E and during charging V greater than E. During discharging, come on, V less than E, during charging V greater than E, correct? Same thing I have written here. So what I mean to say, terminal voltage of a given battery is a variable quantity, it is not a constant, okay. And last, see, to have an EMF with a battery, it is the reason, and because the battery has EMF, you are going to have current passing through it in the closed circuit condition, and then you will have some potential difference between its two terminals, that is you will have some terminal voltage. So production of terminal voltage, it is the effect, and to have EMF, it is the basic reason, okay, root cause. Come on, EMF is a reason and terminal voltage is its effect, okay. If reason is not there, there won't be any effect. If EMF is not there, there won't be any terminal voltage, okay. We begin with question number 13, correct. It is a note on electrochemical cell. Electrochemical cell. My dears, from chemistry, you must have remembered what is called an electrochemical cell. It's very simple. A device with the help of which we can convert chemical energy into electrical energy is called an electrochemical cell. Okay? Just to remember the definition, you please remember that you have to go in this reverse direction, correct? You just go this way and try to define, you will be in a position to give the exact definition. Okay? Simple. A device with the help of which chemical energy can be converted into electrical energy is called an electrochemical cell. Simple. In practice, electrochemical cells are of two types. One is called primary cell, another is called secondary cell. Okay? Now, in textbook, you will not find many points of differences between primary and secondary cell. So, let us go for very good extra question. Mention some points of differences between primary cell and secondary cell. Okay? Hardly some few points are there in the textbook. All these points are not there. Okay? Just pay very nice attention on the screen, please. Here I have written point of difference. Here I have written for primary cell, and here I am going to write for secondary cell. Okay? First aspect for the comparison about chemical reactions. This primary cell is such a cell in which chemical reactions cannot be reversed. You cannot make the chemical reactions, chemical processes being reversed. No. In primary cell, chemical reactions cannot be reversed. Fine. So, I am writing here, they can't be reversed. Okay? But in practice, we require those cells in which chemical reactions must be getting reversed. And for that purpose, we have prepared another type of electrochemical cell that itself is known as secondary cell. So, remember, secondary cell is that electrochemical cell in which chemical reactions can be reversed. So, here I have written can be reversed. Okay? Second point for the comparison, come on, about reactivation. In case of primary cell, once the energy stored in that cell you have completely consumed, after that you cannot reuse it unless and until you refill it, unless and until you just add some reactive components inside it. Okay? So, in order to reactivate the primary cell, we need to add some active materials. We need to add some active materials. Without that, we cannot reuse it. Okay? And so far secondary cell is concerned, in order to reactivate it, what we do? We just pass the electric current just in opposite direction, opposite to previous direction of flow when it was being used up. Okay? When it was in use, at that time whatever is the direction of electric current passing through that cell, just in opposite direction we pass the electric current, and because of current passing in opposite direction, all the chemical reactions get reversed, and then after we can bring it in the original condition and we can reuse it. Okay? Remember, so far reactivation is concerned, in case of primary cell we need to add some new active materials. Okay? And here we need to pass electric current in just opposite direction. Okay? Fine. What about large steady current for long time? If you want large steady means constant, large steady current for a long time, then with the help of primary cell you cannot get it. But with the help of secondary cell, yes, it is possible. So, here I have written is not obtained, here I have written is obtained. Okay? In case of secondary cell, large steady current for a long time is possible. What about electromotive force? Comparatively, for primary cell, EMF is found to be rather smaller, and here rather big values of EMF. Okay? So, here EMF is small, here EMF is large. What about internal resistance? For a primary cell, internal resistance is high, and for this secondary cell, internal resistance is low. Here are written internal resistance is large and here it is small. Okay? Here high and here low. Simple. What about initial cost and weight? Initial cost and weight for primary cell, it is less. For secondary cell, it is more. Here are written more, here are written less. Okay, fine. What about Ampere-Hour Capacity? This term is not there in textbook, just for your kind knowledge. If you are given a typical cell, then you just try to exhaust its energy. You just try to consume its total energy. Okay? And till total energy is consumed, till then, whatever time you have measured, that time you measure in hour, and during that period of time, what amount of constant current you can withdraw from that cell, that you please measure in ampere, correct? So, if current is measured in ampere and time is measured in hour, till the total energy stored in the cell is getting consumed, then after you just multiply current and time. Current is measured in ampere, time is measured in hour. That is why that product I into T is known as Ampere-Hour Capacity. Ampere-Hour Capacity. That Ampere-Hour Capacity for a primary cell is less, for a secondary cell it is more, correct? So, out of all these points of comparison, you can see this is the only point, initial cost and weight, this is the only point for primary cell which is advantageous. All other points are disadvantageous, they are demerits. Okay? For secondary cell, this is the only point which is demerit, and all other points are points of merit. Okay? All other points are advantageous points. So, in all, if you think, then secondary cell is far better than primary cell. Okay? Fine. Now, let us see some of the examples of primary cell and secondary cell. This point also you can add in the points of differences. Okay? No problem. Let me give you some examples. For primary cell, these are the examples, please remember. Voltaic cell or voltage cell, then Leclanche cell, then Daniel cell, then dry cell. These cells which you call pencil cell, which you are installing in the remote control, those cells are dry cells, and each of that dry cell has EMF 1.5 volt. Okay? These are the examples of primary cells. What about secondary cell? Only one example is there in the textbook. It is lead storage cell. Sometimes we call it lead accumulator. Lead accumulator. Okay? Other example which I have given is not there in the textbook, just for your kind knowledge. It is addition cell. Sometimes we call it alkali accumulator. Alkali accumulator. Okay? It is also known as addition cell. So, these two are the examples of secondary cells. Okay? Now, we go for short note on lead storage cell. We have to study now in detail about this lead storage cell, also known as lead accumulator. Okay? I am showing you what is that. These cells are widely used in the four-wheelers, widely used in the cars. In car, whichever battery is being used up, it is this sort of battery, lead storage cell. Okay? Now, here is the construction of that lead storage cell. In a vessel, we just take dilute H2SO4. Aqueous solution of dilute H2SO4 is used as an electrolyte. Because it is dilute, you can understand the amount of H2SO4, which is solute substance, should be less, and amount of solvent, which is right now water, should be more. When solute amount is less, solvent amount is more, then you can say concentration will be less. That is why the solution is dilute. Correct? It is taken as an electrolyte in case of this lead storage cell. And then after we have two electrodes partially immersed in this electrolyte. One is made up of lead dioxide. Lead dioxide. It acts like a positive electrode. It acts like a positive electrode. So, I am writing here plus. An electrode made up of lead, it acts like negative electrode. Okay, fine. So, this is how the construction of this lead storage cell is made. Okay. Now, let us talk about one instrument. It is called hydrometer. Using this instrument called hydrometer, we can measure specific density or specific gravity of this electrolyte. Correct? You must have remembered from 11th standard what is called specific density. Specific density of a given substance is density of that substance divided by density of water. Correct? Remember, density has the unit, but specific density has no unit because it is a ratio of identical physical quantities. Okay? I repeat, density of a given substance divided by density of water will give you specific density of that substance. Okay? Fine. Now, initially for this brand new lead storage cell from which no energy is consumed, at that time the specific density of electrolyte is maximum. It is found to be 1.285. Please remember this numerical value. What is the specific density in the beginning for this electrolyte in case of lead storage cell? 1.285. Okay. At that time its EMF is 2.1 volt. 2.1 volt. Okay. Fine. Now, suppose we want to use this cell. Okay. Then at this moment you please do not consider this outer part of the circuit. Just forget about this outer part. Okay. Forget. And you just consider only this part, that is lead storage cell, and you want to use the energy from this cell. What you can do, suppose you want to enlighten some bulb, then you can just join one bulb here. Correct? Fine. When you join that bulb, then current will flow from positive to negative in the outer part of the circuit. It will flow this way, and because of that bulb will glow. Correct? Fine. At that time current is flowing, look here, this way, means from positive to negative. Okay, this way. Fine. So, at that time current is flowing away from positive terminal. When the cell is being used up, at that time current is flowing away from positive electrode. Correct? Just remember. Now, when that cell is being used up, at that time what happens? Because of the chemical reactions taking place inside, gradually more and more lead sulphate is being deposited on the surfaces of these two electrodes. Correct? For these immersed parts, they will have deposition of lead sulphate more and more as time passes on. Okay? Fine. As time passes on, because of the chemical reactions, it so happens that this H2SO4 is gradually getting consumed. Okay? So, its amount goes on decreasing, that is solute is decreasing, and in that process water is being released. So, amount of solvent is increasing. Just think, when solute is decreasing and solvent is increasing in the amount, naturally the concentration of the solution will decrease, that is specific density will decrease, and by the time specific density decreases to this value 1.15, the cell is said to be getting completely discharged. Okay, fine. So, during discharging process the current was flowing away from positive electrode, and when the specific density of electrolyte becomes this much, cell is getting completely discharged. At that time its EMF is found to be 1.8 volt. Fine. Now, do not bother, this is the secondary cell, it can be recharged, it can be brought into original condition, the chemical reactions inside it can be reversed. But just think with a common sense, if you want the chemical reactions to be reversed, what you should do? You should pass the current just in opposite direction. During discharging process, current was flowing away from positive terminal. Now, during charging process, you should pass the current in just opposite direction, that is, you must pass the current towards the positive terminal. Correct? But then for charging process, you will require that device which has energy more than the energy of this cell, then only that another device can provide energy to this lead storage cell. Okay. For that purpose, we just take the help of some proper DC source whose EMF is greater than EMF of this lead storage cell. If EMF of this lead storage cell is capital E, then this value V must be greater than capital E. V must be greater than capital E, correct? So, you should take that DC source whose EMF is higher than the EMF of this cell, okay? And then after, you should connect that DC source with this lead storage cell in this manner, where you can see this positive terminal of that source is connected with this positive terminal, this negative terminal is connected with this negative terminal. And because this V is greater than capital E, current will flow this way, correct? That is, current is now entering this cell. Earlier current was going away from the cell, now current is entering through this positive terminal. Previously, during discharging process, current was flowing away from positive terminal. Now, during charging process, current is flowing towards the positive terminal, correct? And because you are passing current in just opposite direction, what will happen? All the chemical reactions inside will get reversed. Then, whatever lead sulfate was deposited here on these two electrodes is now gradually getting removed, and in that process, H2SO4 is being produced and the water is being consumed. So, when H2SO4 is being produced, then amount of solid will go on increasing. As water is being consumed gradually, amount of solvent will go on decreasing. Then concentration of solution will increase, that is, its specific density will increase. And when specific density increases from this limit to this limit, when it becomes 1.285, once again cell is said to be in the original condition. It is ready for another use. Okay, fine. This is how you can do the charging of this cell. Because this cell can be charged, it is called secondary cell. Okay. Now, during charging, whatever amount of current is flowing, it is called charging current. Inside the cell, the direction of charging current is this way, from positive electrode to negative electrode. Inside the electrolyte, the direction of flow of electric current is this way. Okay. Suppose this charging process has taken place for T time, then for that T time, this DC source has supplied energy to this lead storage cell, correct? Now, let us find out what amount of energy is supplied, out of that what amount of energy is really stored, and remaining amount of energy which is being dissipated in the surrounding atmosphere in the form of heat energy. Let us find out all these amounts of energy. Okay. Come on. During T time, suppose Q amount of charge is flowing. How much amount? Q amount. Now, what is the potential difference between these two terminals? It is capital V. Then electrical energy supplied by this DC source is V into Q. V into Q, correct? You know, potential difference is work done per unit charge. So, for Q amount of charge, that work done will be V into Q. V into Q. So, this is electrical work done or electrical energy supplied. Okay. Out of this energy supplied, some part is being stored in this lead storage cell in the form of chemical energy. It is E into Q, where E is the EMF of the cell, Q is the amount of charge flowing. Then remaining amount of energy, some part of that is getting dissipated in the form of heat energy in the external resistance. Let it be capital R. Then it is V into Q, but better you write here VR. That is potential difference across external resistance capital R. Okay. Similarly, amount of energy wasted in the form of heat energy in the internal resistance of the cell, let it be V small r into capital Q. Small r indicates internal resistance. So, this is the potential difference across internal resistance multiplied by amount of charge flowing will give you amount of energy wasted in the form of heat in the internal resistance. Okay. Don't you know Q equals to IT, charge equals to current into time. Just place Q equals to IT in all the terms. Come on. Q equals to IT, Q equals to IT. Now, according to Ohm's law, what is the potential difference across any resistance? According to Ohm's law, it is current multiplied by resistance. Current is I, resistance is capital R. And Q equals to IT, put here Q equals to IT. What is this V small r? It is potential difference across internal resistance. Again, according to Ohm's law, it will be current into internal resistance. Current is I, internal resistance is small r, and Q equals to IT. Q equals to IT, correct? Now, this V into I into T as it is, E into I into T as it is, but here I into I, that is I square R T, correct? And here I into I square small r into T, correct? Now, in the same chapter, in the further part of the chapter, we will study about Julienne heat, and its formula is this only, that is current square multiplied by resistance multiplied by time. Current square multiplied by resistance multiplied by time. This is the formula for Julienne heat. It gives you some amount of heat energy. So, this is the heat energy generated in external resistance. This is the heat energy generated in internal resistance. Why do we call these two amounts as wasted amounts of energy? Because of the heat generated in the external resistance, what will happen? This external resistance will get heated up, and from there that energy doesn't remain stored inside that resistance. No, from there it is getting dissipated outside in the form of radiation, correct? So, because that energy is lost by this system, we say it is a loss of energy, okay? So, these two are the amounts of energy wasted in the form of heat energy, okay? And this is the amount of energy stored inside this lead storage cell. It is in the form of chemical energy, okay? And this is in the form of electrical energy. This is the electrical energy supplied, this is the chemical energy stored, this is the heat energy wasted in the external resistance, this is the heat energy wasted in the internal resistance, correct? Fine. Now, throughout the equation, you can cancel I into T, you can cancel. If you cancel I into T from here, left is V, correct? Then here it is E. Then when you cancel one I and T, left is capital I into capital R, here it is. When you cancel one I and small t, then left is capital I into small r, capital I into small r. Simple. I and I you can take common, inside the bracket capital R plus small r. You want formula for charging current I, just make it subject of the equation, transfer this, will become minus V minus E upon R plus R, correct? So, this gives you required formula for charging current. Then you may have one question in your mind, why do we connect this external resistance? If we don't connect, will not do. My dears, here we have placed proper value of external resistance such that this charging current can be controlled. Then you may have a question that what is the need of controlling that charging current? I am showing you. Suppose you don't connect this, okay? Then mathematically R is 0. When capital R is 0, this internal resistance is never 0. This capital R you can keep 0, okay? Then it will be only small r in the denominator, and internal resistance of this lead storage cell is very small. It is as small as nearly 0.01 ohm. Because this small r is very small, then this charging current would be very large. Then you will think that when charging current is very high, what is the harm? Correct? Let it be very high, no problem. The charging process will get finished very quickly. Yes, you are correct. But there we arise across one problem is arising, then we are going to have some more loss of energy. How? I am showing you. Look, when charging current is high, what will happen? This value of I will be high, correct? Now tell me, what is this energy? It is the chemical energy stored in this lead storage cell. So, this is the amount of energy being utilized, correct? Fine, this is useful form of energy because it is getting stored. But there I appears with power only 1, and here I appears with power 2, and both of these two are wasted forms of energy, correct? Tell me, if charging current is very high, then this I square will be very large, here also this I square will be very large, then these two amounts of energy which are wasted in the form of energy will be very large. So, you will have more loss of energy, very small amount will be getting stored, majority amount of energy will be getting wasted. Why should we do that? Correct? We should try to minimize the loss, and for that what we do, we just control this charging current, but for that we need some external resistance. Okay? When you put some proper external resistance, this charging current can be controlled, and then after this wasted amounts of energy can be minimized. Correct? But then you may have another question. You will ask that what will happen to that energy which is produced here in the form of heat energy. My dears, not necessary that you should place only ohmic resistance. You can just place some bulb here. In whichever room this charging process is continued, in that room we need some light, suppose. Then why don't you do one thing? Instead of simple ohmic resistance, you can just put one light bulb here. And when you put light bulb, its filament has got some resistance. And when through that light bulb, when current will flow, that bulb will glow. It will give you some light. So, at least some part of that energy you can utilize now. Correct? Suppose you want fresh air in that room, then you can just run the fan. For that you can just connect here some fan. Then that fan will run, then you will have some usage of energy. Total heat energy will not be getting wasted. If you place here only say resistance, ohmic resistance, pure ohmic resistance, then total energy will be getting wasted. Correct? We don't want that. Okay? So, by placing some proper external resistance, we are going to decrease this, and thereby we are going to minimize this wasted amounts of energy. Correct?